before we get too deep into half-life, let's just take a quick look at property of logs. This is just a quick review of some of the math concepts. One of the property of logs is that, we're going to use natural log in this case, is that the log of two numbers, the sum of a log of two numbers, is equivalent to saying the log of a product of those two numbers, ln xy. This is very useful for pulling numbers out. Again, this is one of the reasons why we could pull out that exponent. Another useful property of logs is that x to the y, natural log of x to the y is equal to y ln x. And so this allows us to pull the y out of a equation, allowing us to successfully manipulate some of these more complex equations. This particular one is very useful for us, as we're going to see in the following examples. A lot of this stems from our first order rate law. Remember, our integrated rate law for our first order is that the natural log of a concentration at some time is equal to the natural log of that concentration at time 0 minus kT. And what you'll find is that you can rearrange this if you know your concentrations to the following. Now, this is where this little fact comes in. We can rewrite this as the following. Ln A at time t divided by A at time 0 allowing us to take this ratio, allowing us to use the ratio. Now, why this is important is because this is a unitless quantity, and so we don't actually need to know what the concentrations are. We can just put in a fraction. So we can say after 75% of the material has been used up, and so therefore we know that the ratio between that there's 25% left, or 99% of the material is used up, or so the ratio is like 1%. And we can plug that into this fraction, and therefore we can then solve without actually having to deal with the actual concentrations. So how long will it take for 75% of the material? How long will it take for half of the material to disappear? This is what we call a half-life. A half-life is the time it takes for half of the material to be consumed, for the reaction concentration to drop by a half, time when half of the material has been consumed. And so we can use this to calculate the times of these materials. We'll just mark it A 1/2, T 1/2 will equal 1/2 A at time 0. That means we can plug that in to this equation such that A at time t would then become the following. Under special cases, when exactly half of the material is consumed, the natural log, well, that's what it says, A at time t is equal to 1/2 A at time 0 divided by A at time 0 will equal negative kT. And so what this means, these are the same. And so we can rewrite this ln 1/2 is equal to negative kT. Well, as it turns out, ln ln of 1/2 is a constant. ln of 1/2 is a constant. ln of 1/2 is equal to negative 0.693. So for any equation, any first order reaction, we can use this idea of the half-life, the time it takes for half the material to disappear. What we find is that the half-life is always the same. It's always a multiple of the rate constant. .693 divided by k will equal T1/2. So for any first order reaction, regardless of the reaction, when half of the material decomposes, it will take exactly, well, this isn't figured in problem 13.92 in your textbook. A good example of this is a 13.29 in your textbook. We don't even need to know the concentrations. All we need to know is the amounts, the relative amounts. When half of it is gone, we can figure out that. That's one of the joys of this form of the equation. As long as we have the ratio, we can figure out the reaction. So if you actually look at this, they have T is equal to 0. There are 15. And at T is equal to 10 seconds, it's 8 yellow spheres. Well, this is a half-life. This is a half-life. Exactly half of the material has decomposed in 10 seconds. 0.693 over T in this case would be 10 seconds, would give us K. And so we can figure out that. We can figure out that half-life from that. We can calculate that and find the value of K. What that means for any first order reaction, though, is that the half-life is consistent. The time between half-lives, exactly half the material will disappear. And probably one of the most simplistic and commonly encountered first order reactions is radioactive decay. So it's very useful, and that's probably where the term where we've heard half-life the most common. So this allows us to predict the half-life. Now, there are half-life equations for 0th order and 2nd order reactions, but they're far less common. What are you doing, cat? They're far less common.